Hello everyone. This is going to be the first of one of some of the new content for the higher course that I'm going to be putting out. Um, this is also one of the first time I've ever done one of these video lessons, so there might be some teething problems, so maybe just kind of bear with me on those, and then we'll see how we get on with this, and then if it's working okay for you guys, I'll look into trying developing some more things that you can work on. So the first part of the higher course that we need to look at is what we call uncertainties, and what they are and how we calculate them. So today, all we're looking at is what different types of uncertainty are and where they come from, and then how we're actually going to calculate the random uncertainty from a set of results. So I'll talk through different types of uncertainty, couple of little examples, and then there'll be a bit of practical work for you guys to do after this in your own time. And you'll have plenty of time to complete it. So there are certain statements that we can make that are exact. So it's an actual fact. So 2 plus 2 is going to give you 4. Or you could say that Mary has 3 brothers. These two things, you could be 100% certain that these are true. However, when we're taking measurements in science, physics, we're not always sure that what we're seeing or what we're recording is exactly what it should be. And so what we say is there's a certain degree of uncertainty, and it comes from a few different sources. So the main types of uncertainty we get come from mistakes. So that's if the experimenter just made a mistake. They come from what we call systematic errors. They come from reading errors, and then we also get a little bit of what we call random uncertainty. So we'll go into these in a little bit more detail now. So mistakes that could be just made when you're taking a reading. So for example, if you were recording a time for someone running, say, 100 meters, and you came up with this set of results, there's one that's standing out in that number 3 here is 108.5 seconds. But because we've taken 4 results and this one's standing out, okay, what we can maybe see is that someone's misread the decimal point and written that down. Okay, so that means that you could, in this set of results, you would be able to discount this, okay, because it's an anomaly. So we take lots of readings. If there's one that stands out significantly, we can discount it, okay, because that's just a mistake. That's a pretty straightforward one. It's quite easy to spot. It's quite easy to deal with. You just ignore it. The next type of uncertainty we get is from what we call systematic uncertainties. And these are uncertainties that will affect all measurements taken during the experiment in the same way. So what we mean by that is that a meter stick may have shrunk. Okay, so all the different values have shrunk by the same amount. Okay, your digital meter might not be correctly zeroed. Oh, that should be zeroed, not zeros. Okay, so if you ever use a set of digital scales, if you touch them as you turn them on and then take your finger off, you'll get like a negative value initially. So then obviously if you were to start checking the mass of things that you put on it, it's going to have a little bit taken off. Okay, so that's why you need to make sure that things are zeroed correctly before we start them. Or the experimenter might be making the same mistake for all the readings. So if we go back to if we think about that previous set of results, if all the times were in the range of, or if the decimal point had been moved over for all of the readings, okay, that would be a systematic error. Okay, so it would all read around 100 seconds. These quite often show up in graphs, in a straight line graph as a change in the y-intercept. So if you're measuring, say, doing an experiment to try and check the speed of sound, what you'd want is you'd have time, say you had time on the bottom in seconds and distance on the side in meters. To get the speed of sound, if at 0 time, you shouldn't move the sound won't have moved any distance, so it should go through the origin here. Oh, so it should go through the origin here and go in a straight line, just increasing up. However, if there has been a systematic error, what you might find is that either your y-intercept is above, which means you've had something added on, or it might be cutting the x-axis here. So if you were to kind of extrapolate this down, it would cut the y-axis down here, and so it would have a value taken off. But every single value, because it's a straight line, has been affected the same way. So that's our systematic errors, okay? So they tend to, as just to kind of reiterate, they tend to show up if you've got a straight line graph as a change in the y-intercept. We can also get reading uncertainties, and so this just comes from how accurately your measuring instruments, the measuring instruments that are being used are. So for an analog scale, so that's just written down numbers, so like on a ruler or a meter stick, or on a speedometer, uncertainty is taken as plus or minus half of the smallest division of the scale. So what I mean by that is, if this is a ruler, we can see here we've got our centimeters, okay, and that's divided into, so each centimeter is divided into 10 subsections. So each one of these would be 0.1 centimeters. Okay, so if my measurement came along to here, I could say that this is 4 centimeters plus or minus 0.05 centimeters. So this 0.05 comes from the fact that, as we said, our smallest scale is 0.1 divided by 2, which gives me 0.05 centimeters. Okay, so I would say that the length I've measured is 4.4 plus or minus 0.05. Okay, so the reading could be anything from 4.35 to 4.45. Okay, so that's for analog, so that's like numbers written down. For digital, we take the uncertainty as plus or minus 1 in the least significant digit displayed. So if this was our timer, okay, the least significant digit displayed is this 7 here, which is 0.01. Okay, so if I had recorded this time, or this is my time, I would state that as 4.87 plus or minus 0.01 seconds. So quite often as well, what they will do is, just to make sure the units are clear, put a bracket around that. So all of these, excuse me, so all of these values are considered to be seconds. So that would be 4.87 plus or minus 0.01 seconds. So that's where we get our reading uncertainties from. The last type of uncertainty we get is what we call random uncertainty. And this comes from the fact that quite often measurements will just change from reading to reading. And so if you were, say, timing the time it took a pendulum to swing, complete 10 swings, you might get a range of values every time you've done that timing. So what we'll do is, to get a best estimate, okay, we take the mean of all the values. So again, we'll repeat the experiment, and then we take a mean of the values that we've recorded. We then find the random uncertainty using a formula that states that the random uncertainty is equal to the maximum value that you've recorded, take away the minimum value that you've recorded, divided by the number of values that you've recorded. It's also often quite written as delta R is equal to R max, take away R min, divided by N. So R max is just our maximum value, R min is our minimum value, and N is our number of values. meet. So just to run through an example of calculating random uncertainty. Times for 10 pendulums, 10 swings of the pendulum are 1.1 seconds, 1.4 seconds, 1.3 seconds, 1.2 seconds, and 1.1 seconds. We want to calculate what is the mean and the random uncertainty. The first thing we'll do is calculate the mean. So the mean is just the sum of all the values. So that's 1.1 plus 1.4 plus 1.3 plus 1.2 plus 1.1 divided by, and we've got 1, 2, 3, 4, 5 values. So that would be divided by 5. So I'll stick that into my calculator. 1 plus 1.4 plus 3 plus 0.1, 5. So that comes out to be 1.22. However, in our readings, we have, we have two significant figures. So I need to make sure that my mean is also stated as two significant figures. So that would be 1.2 seconds. Okay, so my mean value for the time is 1.2 seconds. Now what we'll do is we'll calculate delta R. So delta R is R max take away R min by n. So R max, if we look through, is 1.4. R min is 1.1. And then again, n is 5. So delta R equals 1.4 take away 1.1 divided by 5, which comes out to be 0.06. Now again, we want this to have the same number of significant figures as our final value. Okay, so we have 3 significant figures here, so we want to make that 2, so that would be 0.1. So that means that the time for 10 swings is 1.2 plus or minus 0.1 seconds. Okay, so all we've done is we've taken the largest value from the smallest value, divided it by the number of values we've got. We stated our answer as the mean plus or minus whatever our random uncertainty was. Okay. So now what I'd like you guys to have a go at is a little practical activity, just to do an experiment, find some means, and then state those means with some random uncertainty. So what you'll need is a piece of paper. So I just used a piece of blank paper, a ruler, and some coins. So I've just used a little assortment here of coins. The first thing you'll need to do is create a sort of 1 centimeter by 1 centimeter squared grid on your paper, like so. And then I've put numbers up the side here, just indicating how far they are. So if it's gone this far, it's gone 0 centimeters. If it's gone this far, it's gone 8 centimeters. And what you're going to do is, there's a video on the next slide that I'll show to help this, and then that video will also be in the assignment task. But basically what happens is you put a coin here at the start, just at the edge line, and then you put another coin here. You flick this coin, as it hits off this one will travel up the paper, say land here, and then you're going to measure it. So if we want to measure from the top of the coin, so this one would have gone, say, 8 centimeters. I found that 2p works best as this coin, just because it's quite big, so you've got a good chance of hitting the other coin here. Okay, so if you create this grid, then you're going to flick the coins 4 or 5 times, check your values, put them in the table, and then do your calculations to get the mean and your random uncertainty. Again, these will be, so this, I'll put these instructions in with the slide, but just to show you kind of what to do is that you'll be flicking the coin there, checking where it's gone, and that'll be your result for that coin. If you've got any questions, just drop me an email and I'll try and answer them the best I can. Okay.